Picture this. Your application is humming along on a cloud server. Customers are placing orders, the database is writing rows. Then the instance stops, or worse, it is terminated. The compute vanishes in seconds. So what happens to the data? That is the quiet crisis underneath every cloud architecture. Servers can be disposable, state cannot. A hard drive bolted to one temporary machine is not a durable plan. Something has to separate the life of the data from the life of the machine that was using it. Amazon Elastic Block Store exists for exactly that problem. EBS is high performance, persistent block storage built for Amazon EC2. Think of it as a virtual hard drive you attach to an instance, except the volume can keep living after the instance stops or even terminates. It is tuned for low latency and high IOPS, the kind of random read-write pattern databases love. And inside a single availability zone, EBS automatically replicates your data, so a disk failure does not automatically mean a data funeral. Persistence is the first promise. The second is that you can reshape the volume while it is still running. That reshapeability is called elastic volumes. You can change storage type, capacity, and performance dynamically without scheduling downtime. Backups come as incremental snapshots, stored internally in Amazon S3. Only the blocks that change need to be saved again. Fast snapshot restore strips away the painful initialization delay, so a restored volume is ready at full performance almost immediately. Multi-attach lets certain high-end volumes connect to more than one instance at once. We will return to that because it is powerful and dangerous. Durability ranges from 99.8% up to 99.999%, depending on volume type. And native encryption through AWS KMS covers data at rest, in transit, snapshots, and attached volumes. On paper, that sounds like the whole problem is solved. It is not. Different workloads demand different kinds of speed. Let's slow down on the backup story because snapshots are how EBS turns a fragile disk into something you can move through time. An EBS snapshot is incremental. The first one captures the full set of allocated blocks. Every snapshot after that stores only what changed. Internally, those snapshots live in Amazon S3. You do not manage the S3 bucket yourself, but you inherit object storage durability for the backup chain. Restore used to have a catch. A brand new volume from a snapshot could trickle up to full performance as blocks lazy loaded. Fast snapshot restore removes that initialization delay. The volume comes back ready, as if the performance had been waiting for you. That matters the moment you are recovering a production database and every cold block would otherwise feel like a stalled query. Snapshots are also the bridge across geography later, the only native path the source gives you to carry EBS state toward another availability zone. Here is the central conflict inside EBS. Two families of volumes fight for different jobs. Solid-state drive volumes are built for transactional work, lots of small, random operations, low latency, high IOPS. Hard disk drive volumes are built for big sequential streams, where raw throughput matters more than snappy random access. Choose wrong, and you either overpay for performance you never use, or starve a database that needs it every millisecond. The source draws a clean line, SSD for transactional workloads, HDD for throughput-intensive ones, and HDD volumes cannot be boot volumes at all. The machine that starts your operating system needs the responsive side of the family. On the SSD side, the default hero is GP3, general purpose. It offers single-digit millisecond latency with a baseline of 3000 IOPS and 125 megabytes per second included in the price. Here is the part that matters. You can scale performance up to 16,000 IOPS and 1000 megabytes per second independently of how much capacity you bought. You are no longer forced to grow a giant disk just to unlock speed. For mission-critical databases, think Oracle or SAP HANA. IO2 Block Express goes further, up to 256,000 IOPS, 4,000 megabytes per second, and 99.999% durability. The older IO1 still delivers up to 64,000 IOPS and 1,000 megabytes per second, and is designed to stay within 10% of provisioned IOPS 99.9% of the time. Speed has tiers, so does the bill. On the HDD side, CT1, throughput optimized, is built for frequently accessed sequential work. MapReduce, Kafka, log processing, data warehousing. It can burst up to 500 megabytes per second. SC1 Cold HDD is the lowest cost block option for large datasets you rarely touch, bursting up to 250 megabytes per second. A simple scoreboard helps. GP3 for general workloads at 16,000 IOPS, IO2 Block Express for mission-critical databases at 256,000 IOPS, CT1 for throughput-intensive streams at 500 megabytes per second, SC1 for cold storage at 250. And for new deployments, the guidance is blunt. Prefer GP3 over GP2. Lower cost, independent performance scaling, better flexibility. The fastest volume is not automatically the right volume. Persistence still leaves another question unanswered. What if more than one machine needs the data at once? Standard EBS answers with restraint. An EBS volume attaches independently to its host EC2 instance, typically a single instance attachment model. Amazon Elastic File System, EFS, plays a different game. A shared file system that many servers can mount concurrently, even hundreds of them. Picture it. EFS is one shared folder in the middle of a room. EBS is a set of separate virtual disks, each handed to a machine. That design keeps block semantics simple and fast. It also means ordinary EBS is not a casual shared drive. When teams need true multi-writer block access, EBS offers a special door, and that door has a warning sign. That door is multi-attach. On provisioned IOPS volumes, IO1 and IO2, you can attach one volume concurrently to up to 16 Nitro-based EC2 instances, all inside the same availability zone. On a whiteboard, it looks like freedom. One authoritative disk, many compute nodes. In production, concurrent writes without coordination will corrupt data immediately. Multi-attach is only safe when a cluster-aware file system, such as GFS2 or OCFS2, serializes and coordinates those writes. Flexibility without discipline is not high availability. It is a race condition with a permanent scar. So EBS can stretch beyond one machine, but only when the software stack above it understands that many hands are on the same disk. Where does this quiet layer actually show up? Everywhere state has to survive a reboot. Self-managed MySQL or PostgreSQL on EC2 sits on EBS volumes. Managed services are not exempt. EBS is the underlying persistent foundation behind Amazon RDS and Amazon Document DB. And when containers grow up into stateful workloads on Amazon EKS or ECS, EBS supplies durable volume mounts so a pod restart does not erase the database files. Most users never see the block device. They see an order history that still loads after a deploy. That is the point. EBS is infrastructure under the application story. Persistent, tunable, and, if you configure it, encrypted by default. The source's recommended habits are less glamorous than the headline features, and more important. Enable encryption by default at the account level, so every new volume inherits KMS protection without a heroic checklist. Prefer GP3 over GP2 for granular IOPS and throughput without padding capacity. In Kubernetes on EKS, deploy the official Amazon EBS CSI driver, so volumes provision and mount as part of the cluster's normal lifecycle, not as a midnight manual chore. And when Elastic Volumes let you grow a disk on the fly, remember the second half of the job. Extend the operating system partition and the file system afterward. Resizing the cloud object is not the same as giving the operating system permission to use the new space. Miss that step, and you have paid for capacity the application cannot see. Two operational details decide whether EBS feels magical or misleading. First, billing. Object storage like S3 tends to charge for what you actually store. EBS charges for what you provision, size and allocated performance, even if the volume is mostly empty and the IOPS sit idle at 3 a.m. That is not a gotcha if you plan for it. It is a gotcha if you copy S3 instincts into a block volume. Second, growth. Elastic volumes let you expand capacity or shift performance without detaching the disk. But the cloud control plane and the operating system are not telepathic. After the volume grows, you still extend the partition and grow the file system inside the guest. Skip that, and monitoring will show free space the application cannot write. Teams that automate only the AWS API half of the resize discover the other half during an outage. Pair provision-aware capacity planning with a complete resize checklist, and EBS stops surprising you on the invoice and on the disk full alert. Every strong abstraction has a boundary. An EBS volume is bound to one availability zone. You cannot simply attach it to an instance in another zone. Billing is provision-based. You pay for the size and performance you allocated, whether or not the bytes are hot. Multi-attach without a cluster file system means immediate corruption. That warning deserves repeating because the failure mode is silent until it is catastrophic. And there is no native multi-AZ replication. If an entire availability zone fails, EBS will not magically appear healthy next door. Cross-AZ recovery is a design you build with snapshot copies, not a checkbox on the volume. Local speed and local durability are real. Geographic resilience is a separate decision. Zoom out to the failure mode architects actually fear. Not one disk, but one whole availability zone. EBS replicates inside its zone. That protects you from hardware hiccups next door in the same building complex. It does not protect you when the zone itself is the blast radius. There is no native multi-AZ mirror on an EBS volume. The recovery path the source describes is deliberate and slightly manual in spirit. Take snapshots, copy them to where you need them, and rebuild volumes in the surviving zone. That is why multi-tier apps pair EBS-backed data services with snapshot policies, infrastructure as code, and sometimes higher-level services that hide the choreography. RDS can feel multi-AZ while still resting on EBS underneath, because the managed layer owns the failover playbook. If you roll your own database on EC2, you own that playbook yourself. Local block speed is the prize. Cross-zone survival is the homework. So return to the opening stake. The server can disappear. With EBS, the data does not have to disappear with it. Compute becomes replaceable. Block storage stays persistent, encrypted, snapshot-backed, and tunable. From thrifty cold HDD up to IO2 Block Express for the databases that cannot blink. Multi-attach and elastic volumes add flexibility if you respect their rules. What remains unresolved is the tension the architecture never fully erases. How do you keep the low latency feel of local block storage and still survive the loss of an entire availability zone without elaborate snapshot choreography? That is the question careful architects still answer with patterns, not with a single magic volume type. EBS solved the disappearing disk. The disappearing data center is still on us.